So today, mostly this will be the last class, and we will mainly discuss whatever is remaining of these servo motors and primarily different encoders and other sensors which are used in precision machine development. So that's what we have decided for today. So we discussed how servo motors work and what are the key components in servo motors. One of the key items in servo motors is something called encoders. And this is, I'll introduce encoders today, and then the next presentation which we will do, hopefully today we'll finish it, would talk in detail about the encoders. So that's what is the plan for today. So basically, if you look at it, servo motors are different from typical motors as there's something called they have encoders. And this encoder, what it does, it actually enables high speed and high precision control if you give the position and speed controls. So this encoder can actually be used to measure position and speed, both. Okay. And encoders are one of the hardware elements that form a core of a servo system. So that's something which is the key part of a servo system. A servo system needs to have an encoder, and they generate speed and position feedback. So that's something which is required. And in many cases, encoder is built into the servo motor or somehow attached to the servo motor. But in most cases, if you buy a servo motor, encoder will be built into that motor. And in certain applications, the encoder is independent unit installed away from servo motor, and it is installed in a, sometimes it may be installed in a remote location away from the motor. And there are two different kind of encoders. The first one is called incremental encoder. I'll talk in detail in a little bit, but I'm just giving you some brief overview, and then we'll discuss in detail incremental and absolute. So anybody can tell me what will be the difference between incremental and absolute encoders? What do you think will be the difference between, say, if I talk about incremental encoders and I talk about absolute encoders? How will they be different? Any ideas? Anybody? How do you say this is an absolute encoder and this is an incremental encoder? What will the fundamental difference between the two? Between the absolute and incremental encoder? Somebody should guess, right? One of you. At least the name suggests, right? The name suggests that there is absolute and incremental. So what would be the fundamental difference between the absolute encoder and the incremental encoder? You can either say it out aloud or you can type it in the text box, whichever way you are comfortable. Anybody? I'm sure you guys know the difference between absolute and incremental, right? What would incremental do? What will absolute do? So this is a general statement which you have made, that incremental gives a change in something and absolute gives its value, right? But what will it mean in terms of motor? In terms of motor, what will absolute give you, which incremental won't? This is the right definition, but in terms of motor, what would the absolute give you? The position of angle through which the motor has rotated. Which one will this give you, incremental or absolute? Incremental or absolute? The incremental will also give you, the incremental may not give you position, exact position. That's what the absolute does, because absolute gives you exact position. The amount of angle which the motor is rotated is given by incremental also. So there is a reference point in incremental which would tell you how many pulses. It will count the pulses. I'll actually talk in detail about it. It will count how many pulses it has seen. So it will know what is the total angle it has moved. It will also be given by incremental. Incremental will also give you how much angle it has moved. The problem is it doesn't know exactly what is the position. So what absolute does is absolute actually creates the exact position, because for every location in an absolute encoder there is a unique code. So I know exactly where you are. That's the difference between increment. In incremental, I count how many segments, or I'll just count pulses for every segment. So I know what angle I have turned. That I know in incremental also. But in absolute, I know exactly where I am, because each signal is unique. I'll show you how it is in a little bit. But this is what I wanted to kind of prime you before we move on to the next thing. And there are multi-turn absolute encoders which are typically used for servo motors. And these are, I'll show you how multi-turn absolute encoders, what do they mean and how do they work. I'll talk about it. So servo drive. So encoder is one part. The other important part is something called servo drive. Okay, looks like still not visible. My slide is still not visible for some reason. Can you see the servo drive slide? Yeah, yes. So servo drive follows commands from the host controller and control the output torque, rotation, speed, or position. So servo drive is another integral part. So as I told you, there is a servo drive and then there is a motor. So motor comes with a drive. And this drive is called servo drive. It follows the commands from host or controller to control output torque, rotation speed, and position. The position, speed, and torque are controlled according to the inputs of motion controller. So motion controller can be a software which will interpret the G codes. It will interpret the G codes which you give, and then ask the motor to move, right? And then there is a feedback encoder. So the feedback signal would come to the servo drive. The servo drive supplies the appropriate amount of power, because what happens is the computer controller will give only 5 volts, but that is not enough to drive the motor, right? So it actually will amplify this signal and have enough current, enough appropriate amount of power to drive the servo motor. And the basic operating principle is same as an inverter, where it takes AC power to DC power at certain frequency. So if you see, what it does is it gets, this is the supply frequency, 50 or 60 hertz, depending upon where you live. If you live in India, it's 50 hertz. If you live in America, it's 60 hertz. And then what happens is, what you give is at 0 to 400 hertz. 400 hertz. And there is something called pulse width modulation. Pulse width modulation, which is used to control. So control is done by pulse width modulation. And there is converter circuits, smoothing circuit section, and inverter section. And then this is basically what is used to control the servo drive. So basically, pulse width modulation will, your servo drive contains control circuits and the other circuit which will do what is it called, your current circuit, which is like an inverter, smoothing, and so converter, smoothing, and inverter section. So this will be one section which actually converts 50 hertz to 0 to 400 hertz, which will finally go to the motor. And the control circuits, which will take signal from encoder and just give the error signal to, and amplify the error signal to control the position. So this is the sensor. This is the sensor feedback. Sensor feedback. This is the sensor feedback. Sensor feedback. And this is what drives. You need to drive the motor, right? Move the motor faster, slower. So this drive current is given by this section. Drive current. in a servo drive. Servo drive is like a big box, which I showed you in the last class, right? And in the last class, I actually showed you how a servo drive looks. It's a nice big box. Okay. And the functions of servo drive is this: it communicates with the motion controller, meaning this will be the motion controller will be in your computer. It communicates with that. It actually takes encoder feedback reading in real time for closed loop control, and it does input output processing for safety components, mode inputs, and operating status signals. So that is what it does. Commands are given by your interpolator, which is there in your, which will be a basically your control software in which you write G codes, right? And those G codes are processed and commands are given to this servo drive. So G code says if you want it to go from point A to point B at certain speed, this you write it in your computer in the form of G codes. This is interpreted and passed on to the servo drive. And if I'm not there, the feedback will come from the sensor, from the encoder, that okay, you need to go faster, or you have reached, so stop. So all these signals will come, and the driving will be done by the servo drive. So basically, your control loop adjustment and power to the to drive the motor both comes from your servo drive, right? But all the processing is done in the computer. That okay, you have to do this step. So this motion has to be done. This interpolation is done in your computer, right? And that is passed on to the drive. Okay. So if you want to select the right motor for your task, I just go through a flow chart. The flow chart is, first thing is you have to, has the machine been selected, right? What kind of machine you have to use, right? And then what has the operating pattern? How do you want to operate? How do you want to operate that machine? So basically, I'll just read out for you. Machine means the size, mass, coefficient of friction, external forces of the moving part of the servo motor rotation, of which, so basically you need to know the area, the size, the mass, the coefficient of friction, and external forces of all the moving parts. So that's what the machine selection means, right? The size, the mass, the coefficient of friction, and the external forces. These basically constitute what my machine will look like. And then operating pattern, which basically means the relationship between the time and speed. How do we have to, do you have to ramp it up very fast, or you have to ramp up slow, or you have to ramp up very fast and then go steady state, go at constant velocity? So what kind of motion is required? Whether you have to ramp up, you have to go steady, ramp down. So whether you have to go triangular, or you have to go trapezoidal. These are the primary two types of operations which you do in machine. And then calculate the load inertia for motor shaft value. So you basically want to understand how much the motor shaft will be exposed to, and calculate the added load torque for motor shaft. So basically, at some point you need to know the torque, because my torque times RPM is what will govern the motor power. So I need to estimate the torque. So can someone tell me, where does the torque come from? So if I'm driving, say a lead screw or a ball screw, right? A ball screw. Where does the torque come from? So there is a ball screw, right? And this ball screw, on the ball screw there is a load mounted. So there's a load on the ball screw. This ball screw rotates, and then the nut will move on top of it, right? And there will be physical motion of that. How does the torque? How do we estimate the torque? How would the torque come? What kind of torque is required? How do I estimate it? Because torque is what will basically define the power. So I need to know what torque. How do I estimate my torque for a given ball screw, or for any other operation? So where can torques come from? Any answers? Very good. For a constant speed of operation, you're right. Constant torque can be come from friction. Friction torque is the right answer, but it's a very good answer. But what happens is there will be external torques also, right? If I'm loading, and if it is if so, say I'm using this stage for machining, right? So imagine my tool is moving in this direction, so my tool is also applying external torque. So even if I am moving at constant speed, other than friction, there can be external torques also. External torque can also be there, right? Yes or no? So imagine I am actually moving at constant speed, but I'm also cutting. Say I'm doing a shaping operation, right? So let's imagine I'm doing a shaping operation perpendicular to the motion. Let's imagine that we are doing something like this. So there will be a torque which the motor has to overcome. So there, the total torque will be function of the external torque and the friction. But if I have no external torque, or no inertial force, as you said, at constant, so there will be inertial force, which is because of acceleration, and that can create torques. There can be frictional force, which will always be there. That's the minimal load, which will always be there. And the third one will be external torque. So all these three we have to combine and find out what will be the torque there. So basically, my ball screw or lead screw or my motor, eventually my motor has to take that kind of a torque, whatever is being exposed to that. So the external loads, the friction, and the inertial forces, all three would be there, right? And then that's how you size your motor, right? So you size the motor temporarily. Then you look at acceleration and deceleration torque, because that will basically how you're accelerating will have some inertial forces and torques. And then you basically design the motor for maximum torque, because your motor should be able to take, it should not stall. If I have a torque which is more than what motor can give, the motor will stall. Stalling means it will not be able to rotate. That condition you don't want. You don't want your motor to stall. So you have to calculate your torque. In fact, it should be more than you require. It's okay. Right. So oversizing motor is actually a smarter thing to do as opposed to having an undersized motor. Okay. So this is where we will stop for this. And then let's go on to the next one, which will be primarily about encoders. So that was the first portion. Today, mostly we'll finish the curriculum. So next thing which we will talk about would be the other thing, which is encoders. So I wanted to talk a little bit about encoders, because this is something which probably is worth knowing what to use where. So basically, when we talk about sensors, especially in design, primarily we'll talk about mostly these will be encoders to know and control the position, to know and control the machine position, control the position and speed. We can say we can do also torque control, but typically we'll say position and speed. The position and speed, because most of the machines which design, right, it will always have some positioning, whether it's a robot or a gantry system or a machine tool system, or even anywhere where you need power, right? You need motors, and you need to have, if you want to use it for motion, you need to be able to sense it. So the first class of encoders are something called optical encoders. If you need very precise location, there's something called interferometric sensors which you use. These are used only in lithography systems, very, very precise systems. Then there are other ways to do it. There will be laser triangulation, focus variation. They typically are not used for machine operation, but triangulation people can use for machine. Focus variation is not for machine, but more for metrology, more for measurement. But I'll still talk about it. So basically, There are optical, there are interferometric, there are triangulation sensors, laser triangulation sensors, and focus variation. So these are some of the sensors we will talk about today in this class, and this will be the last class today. So let's discuss a few things. So encoders are digital transducers that are used for measuring angular displacement and velocities, both. So we know at what velocity I'm rotating, what is my angular velocity, and what is the total displacement. So there are three basic kinds of optical encoders. There is optical, which is called photoelectric. There what happens is there is a light sensor and there's a light source, and you can either have alternate dark and bright patterns, or you can have holes. So every time there is a hole, the light passes through. If there's no hole, there is an opaque thing that doesn't pass through. So this will give me a signal. This will give me a pulse signal. So I can have something like that kind of an effect. Or I can use a magnetic encoder. Magnetic encoder is nothing but it will give me magnetic fields and it will give me pulses again, as and then I pass that field. Or there can be a mechanical contact where I can have these bumps and high points. Remember the old school gramophone player, right? That was actually a mechanical contact encoder. So basically at every location there was contact breaking, contact having breaking, so you were getting a signal, and the signal corresponded to the music. So that's a mechanical contact kind of a encoder. That's actually an encoder if you think about it. It gives you a signal. So shaft encoders are digital transducers that are used for measuring displacement velocities, and relative advantages are high resolution. You can get very high resolution depending upon how many of those you have, like at what is the frequency of those holes or your alternate dark and bright patterns, and high accuracy because due to noise immunity of digital signals. So mostly now they're not analog things, they're all digital. So basically it's very highly immune to noise. So it's actually a good quality signal you get. And relative ease of adaptation in digital control system. So basically all the controls today are digital controls. So basically since you get a digital output from it, it's pretty good. So there are two basic things, incremental and absolute, and I'll talk about how absolute is different than incremental. So incremental output is a pulse signal is generated when the transducer disk rotates as a result of the motion that is being measured. By counting the pulses or by timing the pulse width using a control signal, we can know angular displacement and angular velocity. Displacement, however, is obtained with reference point on the disk, right? So the index pulse counts the number of full revolutions. So there are two challenges with this. I don't know which way I'm rotating, positive and negative, right? And the second thing is if I miss one or two pulses, I'm off. I'm always erroneous, right? So there are some problems with this incremental encoders. First, let me show you how incremental encoders look. This actually, I'm sorry for this. So let me do one thing. Let me share something else. What I will do is I'll stop sharing here. I'll share something else. Just give me a minute. I'll share here. Just 1 second. Just 1 second, I'll just share the screen with you. So this is a much better picture. So what you see is for an incremental encoder, this is how it looks. This is how it looks. It has, say, a slit, and then there is a LED light source and there is a sensor. So there's a light source here, there's a sensor here, and you get an output. So every time the light passes, you will get a photo. There is a photo transistor, photo diode. So it will give you some voltage every time the light hits there. So you'll get pulses. So you'll get one pulse, the next pulse, the next pulse, the next pulse, which basically means that I am, and this I know because I know what is the difference between two of these pulses, right? So I would know I have rotated this degree between this and this. I know the angle between the two because I have fabricated the encoder. That information is there with me, so I can know where it is. So this is encoder track, and this is the output. So this is what a incremental encoder mean. So one track and one peak of encoder. This is what it is, right? So every time it hits the slit, there is a power. There is a pulse. You get a voltage pulse because of this photodiode or phototransistor. But let me see other end. So this is what. So this is a sliding contact encoder. If you see, so there would be basically a sliding brush which will go, and every time there is a contact. So this is conducting. The other one is insulating. So every time we fall on the conducting one, this is the mechanical encoder. You would get a pulse signal. But these are obsolete now. Most of the ones which you use, and magnetic, still people use magnetic encoders, but optical are the most high quality. Okay. But magnetic encoder is again very similar. So you will have a magnetic spots there, and you basically pick up whenever you hit the magnetic spot, right? So that whenever you get close to this magnetic spot, you will get a peak. So basically, pulse values in the magnetic area, pulse peak would be in the non-magnetic area. That's how you would actually get the data. So you get peak and you get valleys, so you can count out your the magnetic thing. The principle is a proximity sensor based on magnetic induction, right? So there is magnetic and optical encoders, but most of the ones. And then this is also again incremental encoder, but there is a reference window. So you would know where you are. So every time one rotation goes through, you will have a reference window. So basically you pick this, and then you'll pick one of these, and the next rotation you'll pick this again. So this will be your reference window right here. And this will be your, so you can basically know how many rotations you have done, right? So that is what is called basically a reference window, if you would like. So you can get a reference pulse. But the problem with incremental, let's talk about what are the problems with incremental encoders. The detection of rotational encoders can be a problem since pulse don't indicate direction. So you basically you don't know whether you're going in clockwise or counterclockwise direction. But you know that if I have to control the motor, I need to control in both the directions, right? Because I need to go front and back. So I need a bidirectional control. So the bidirectional controllers will have two tracks, which will be 90 degree out of phase with each other. So that will give us some degree of bidirectionality. So that's where the incremental encoder is there. But again, the problem of missing a few will still be there because there is no unique correlation with the encoder. So every point doesn't have a unique signature. So that's what is there in a absolute encoder. So absolute encoder has many pulse tracks on its transducer disk, And when the disk of an absolute encoder rotates, several pulse trains equal to the number of the tracks are generated simultaneously. So basically, let me not read out, but show you what it means. So imagine you have this kind of encoder where there are 1, 2, 3, 4 tracks, right? If you have these 4 tracks, basically means that I can have this color coding. One can be dark, one can be bright, right? So how many total things I can have? 2 here, 2 here, 2 here, 2 here. So I can have 16 combinations. For 4 track, I can have 16 2 to the power 4 combinations. For 5 tracks, I can have 32. For 6 tracks, I can have 64 combinations, right? 64 unique combinations. And every location, you look, every location is unique. So my 0, 0 is all 4 dark, right? My 1 is 1 bright, first bright, all 3 dark. Second is second bright, all 3 dark. Third is first bright, second bright, all other 2 dark. So I can have all these unique combinations. Now the beauty of this kind of a system is every location is now uniquely coded. So I know the exact position where I am. So basically, if all 4 are bright, meaning I will have a binary code for this. The binary code will be 1, 1, 1, 1, right? And for this one, the binary code will be 1, 0, 0, 0. So for each location, I have a unique binary code depending upon number of tracks, right? So for a 4 track, I can have 16 positions which I know. So my resolution will be, my resolution is this, basically 1/16 of whatever the total rotation is, right? And I can have one more track, become 1/32. I can have one more track and I can become 1/64, right? And each position will be unique, right? A bit switching may not take place simultaneously. So you can also have a step better than this, which is called a grayscale code. So you can have use a grayscale code to do something called binary. So basically, what happens is, so a bit switching can be avoided by using a gray code. So that's a step further than a binary code, right? But absolute code must be powered and monitored when taking a reading. Also, if a reading is missed, it will not affect the next reading. But the trick here is that you need to have, the machine powered, because you have to take the signal and you have to monitor the signal. So this has to be, encoders should always be powered and monitored when a reading is taken. That's the additional thing in a what is it called, in a absolute encoder. Any questions here? Do you have any questions about absolute encoder or incremental encoder? Okay. So let me just, since I've explained now, so I'll go through the absolute encoders. Absolute encoder has many pulse tracks on its transducer disk. So unlike incremental, where there is just only one pulse and one reference, one pulse track, the disk of an absolute encoder rotates. Several pulse trains equal to the number of tracks are generated. So you generate basically a bit code, right? So you have a binary 4 or 5 digit number of tracks, whatever the number of tracks are there, you will get that many numbers of binary code. Okay. At any instant, the magnitude of each pulse signal will have one signal level. That is a binary state. You have a level detector. So you'll get 0 and 1. So you'll get a combinations of 0 and 0, 1 for every track, right? For every track, there will be either 0, 0, either 0 or 1. And you can know where exactly you are at a given location. The pulse windows on the tracks can be organized as some code so that each of these binary numbers correspond to the angular position of the encoded disk at the time when the particular binary number is detected, right? So now that's the property of your encoder itself, because at every location your encoder spits out a unique code. Pulse voltage can be compatible with some sort of TTL, which is basically nothing but a TTL is basically a pulse signal. Direct digital readout of an angle position is possible now. So you actually know exactly where you are using an absolute encoder. Absolute encoders are commonly used to measure fractions of revolution. However, a complete revolution can be measured using an additional track that generates an index pulse, as you have that reference pulse as you have in case of an incremental encoder. You can have just one to basically count the rotations also. So this we have already discussed. There is another thing in an incremental encoder, something called quadrature. So in quadrature, what you do is you will have tracks V1 and V2 tracks. So basically, what you do is you have either 90-degree lag or lead. So earlier, what you can do is you can just count each increment, right? So your resolution is just this, right? How many pulses you get? How many pulses you get in one rotation will be your resolution. But if you just keep one more thing at 90-degree lag or lead, then what you can do is you can get states where the first one would be this plus this, which is, so you get one signal and then again you'll go to 0. Then again you will go to the next state, right? So basically now you can get signals from both, one with 90-degree phase lag. So instead of getting the information, what you are getting one pulse, so in one cycle you get 4 signals there, right? So if you see first 90-degree, let me just actually switch here so that this will be more clear. Just give me a minute. Let me see if this is. This I think I'll use to. I'll have to write on it. It will be better. Just 1 second, just let me bring that here. Okay. Yeah. Let me share this slide here. Just 1 second. Yeah. Hopefully you can see this on your screens. Can you see this? Yeah. Right. So this is the quadrature I was talking about. So right now, if I were to do it normally, right, I will have, this will be my resolution, right? So how many over pulses I get in one rotation? Number of pulses in one rotation would be my pulses per rotation is my resolution. Sorry. Number of pulses per rotation is my resolution. Is my resolution. Right? Now, if you imagine, I have now, what I did was I have either 90-degree lag or 90-degree lead. So this one is 90-degree. The first one is 90-degree lag. 90-degree lag. So basically what happens is this one. So in first 90-degree, I will get this signal. I will get this plus 0 here. Right. So this will be my first transition. I will have this signal and then there will be another transition here, 0, 0. So I will get first transition here. Then again, what will happen is I will have the second transition. So this will be first, this will be second, this will be third transition right here. And now in 360-degree, I will have another P, 4 transitions. So I can sense in 360-degree, I can sense 4 as opposed to only 1. Here I was sensing if I didn't have this quadrature in 360-degree, this is 0, this is 0, this is 1. So I get only one transition from 0 to 1, right? But the moment I have this 90-degree lag, I get, sorry, I get the first transition will be, so this is the first signal I get. The second signal I'll get here in this range. So there will be this transition, right? So I can count this and then 0. So there will be 1 and 0. So 0, the second one. Then again there will be another increase, right? Another increase because this will again be a non-zero. So third, and then again fourth will have further increase. So now what I can have is I can have 4 states here. Instead of having 1, I get 4 states. So by using quadrature, my resolution can become 4 times. With just one additional track, which is 90-degree lag or lead, I will get 4 different transitions. And I can sense that because this is the current, right? So I can sense 0, more, so 0, non-zero, then again, so this will be non-zero, 0 here, then again non-zero, and then another pulse which is higher than both, right? What you are seeing is double pulse. So I can actually, if I sense the current values, I will have 4 different current values: 0, first x, then 0, then x, then 2x. So I have these 4 different states just by using one at 90-degree phase, either lag or lead. So this is called quadrature. And what this does is this gives me that this multiplies my resolution by 4. So if I have an incremental encoder of say 1000, right? 1000 points in one rotation, 1000 resolution is there, 1000. So I can have, say, in one rotation, I can have 1000, what you would say, some 1000 pulses. But if I do quadrature, I can multiply it by 4. I'll have a 4000 pulses then. 4000. So my resolution will increase by 4 times just by using this quadrature. Okay, this is what I wanted to share. What I will do is I will go back to the share again, and then we'll share the So this is what I wanted to talk about when I talked about this quadrature. Okay. Right. So the next is something called maximum count possible. So m pulses, if you have theta max, this maximum count is basically n pulses by maximum count possible is basically is a function of theta. So if theta max minus theta so basically by number of pulses will be how much you can have maximum count possible. So maximum count is theta, theta minus theta max by number of pulses is what is m. And then the range of encoder is plus minus theta max. If the size is r bits, m is 2r minus 1, zero count is also included. And if zero count is not included, m is 2r minus 1. And basically conventional definition for resolution is theta max minus theta min divided by 2r minus 1 minus 1. This is the formula for actual resolution. Okay. And these are the things which when you go and buy an encoder, these are the things which you should know. The first thing is called accuracy. Accuracy is the measure of how close the output is to where it should be, right? So basically it expressed on unit of distance such as plus minus 30 arc seconds or plus minus 0.0001 inch. If it's expressed in percentage, make sure to state whether it's a percent of full scale or percent of nominal resolution. So that's very important. But ideally, when you ask for accuracy, you should ask for exact unit distance, whether it's rotary arc seconds, linear in inches. And bit is the abbreviation of binary digit. It refers to the smallest element of resolution. Error is the algebraic difference between the negative value and the true value of the input. And there is something called frequency response. The frequency response of the encoder is the electronic speed limit. How many it can log in 1 second. So 1000 cycles or how many cycles. So basically, this is important because that's how I'll be able to get data in one revolution, right? So the rotation speed must be in revolutions per second or RPM, and linear speed should either be in inch per second or millimeter second, depending upon the scale count. So you should also, when you should also know its frequency response, right? How many points I'll get in one cycle is very critical in having so that also is very important, that I in one rotation I get many, but then I'm also limited by how many data points I can capture in 1 second, right? In one rotation I can get 16 or 20 or whatever or 100, but then how fast can I extract that information is the frequency response. Then there is index signal. Index signal is basically once per revolution. So it basically gives you how many turns you have made, right? Then there's interpolation. Involves an electronic technique for increasing the resolution from number of optical cycles on the disk to higher number of quadrature. So using quadrature, you can interpolate and find out what is how many. So this will enhance your resolution of the thing once you have this interpolation. Measuring step is what is the smallest resolution quadrature can decode, right? Not the actual location of your pulse generator or your slit, but the quadrature step, because you can always have 1/4, right? It's also called quantum. There is pulse per revolution commonly, but when used to cycles per revolution when quadrature square output is there. Quadrature I've already explained that it's 90-degree phase relationship between A and B channels of an incremental encoder output. And there is quadrature decode, which refers to the common practice of counting all 4 quadrature strings, right? So if you have 1000 cycles per second revolution encoder, the quadrature will have 4000 cycle counts per second. Okay, because you will get wave transitions, 4 transitions per wave if you have this 90-degree lag or lead. There's something called quantization error. This quantization error is inherent in our digital system. It reflects the fact that you have no knowledge of how close you got to a transition. It's commonly accepted as plus minus half bit, right? Because there's a finite width in every pulse, right? So there will be some error there. So you assume that error is plus minus half bit. Repeatability is measure of how close the output is this time to where it was last time, right? If you ask it to go to the same location 5 times, what is the error in each is repeatability, right? Resolution, on the other hand, is the smallest movement detectable by the encoder. So resolution means nothing. It's just that I can sense that much. But whether my machine can do that, I don't know. You get me? So resolution can be very misleading. Resolution is what I can detect using my encoder. That doesn't mean that I can position to that accuracy. So there's a difference between resolution and accuracy. Accuracy is I can actually position with that accuracy. But resolution is I can see accuracy. So accuracy is always more than resolution. You have to remember that I can sense very small amount. So I have a sensor which can sense 5 nanometers in my linear motor, but my error is roughly 100 nanometer. Okay, just because I can sense a very small amount doesn't mean I can control it and accurately position my stages. So there's a difference between the two. There's something called slew speed. Slew speed, the maximum allowable speed from a mechanical consideration, and that is determined by the frequency response. I cannot go anything more than that. I'll not have any meaningful data from my encoder if I go beyond that. That's the slew speed. And then there are linear encoders. So linear encoders actually are for more precise location. This you have, if you use a rotary encoder, you do a semi-closed loop feed. It's a semi-closed loop feed, and if you want full all tight servo loop, basically fully closed loop control, then you need a linear encoder. This linear encoder gives you the position, exact position. Right. Optical encoders are also used. Interferometric techniques are also used. Magnetic encoders are also there. So optical, magnetic, and interferometric, all three linear encoders are there. And then there's something called image scanning. So this image scanning is function of projected light signal. So basically there is something called Bragg's grating. So if you have this grating, you can have two gratings. So there is first grating and the second grating. And the difference between these gratings, one grating moves over the other grating, and then you get a signal. This is for very precise positioning. People use a diffraction grating to position accurately. So these are another set of techniques. So basically what you do is, this is what is there in lot of these linear encoders, precise linear encoders. So there will be one grating which will be fixed, one grating which will move, and then you will get lights, dark and light surfaces at different distances. And this is how you locate when they move. When the gratings move into each other, the incident light is modulated, and this modulation gives you your actual positioning. Okay, so that's what a linear scale does. It has two gratings which move, and these gratings will basically create different sets of modulated light, and the photovoltaic cell can convert these variations of light into the electric signals. And there is interferential scanning probe. This is done when you have very small grating. You require very small resolutions. So basically in this, what you do is you do something like this. You have interferometry, basically meaning that you will have interference between the waves, and you will get alternate light, dark and bright stops because of interferometry, right? Because the light travels different paths, so there will be constructive and destructive interference, and this will create a measure of the distance. So what is the distance between the two? You can measure based on the. So if there is more distance, then what you will get is you will get different fringe patterns. The fringe patterns will give you what is the displacement. You can actually measure roughnesses of the order of, I would say, they claim to measure sub-Armstrong. 0.1 Armstrong is what they report using an interferometer, a wider interferometer for roughness measurement. So that's the accuracy that you can get from an interferometer. I'm just giving out those numbers to you. You can actually measure a atomic flat. You can measure what is the roughness of an atomic flat using this kind of a technique. Then there are magnetic encoders. The magnetic linear encoders read basically element in connection with a scale that is magnetically coordinated with alternating polarity. The alternate north and south poles are spaced at precise distance, and that will be a pitch. So every time there is a switch in the polarity, you can get the voltage or change in magnetic resistance, right? Magnetic encoders we have used in our machines, they are usually less precise than an optical encoder. Optical encoder is more expensive. And then there is laser interferometer. This again works on interferometry, which I showed you in the previous time. But these are very, very precise. As I told you, you can actually, again, this is because you have two different paths of light, one less and one more, and they basically, those light will constructively interfere if there is, under what condition the constructive interference will take place? Can somebody tell me that? What is the phase difference between the two lights? When does constructive interference take place? What should the phase difference between them? Tell me. N lambda and destructive? Very good. So it should be basically number of wavelengths. So if multiple wavelengths will always have considered interference. And what will happen in destructive? When we'll have destructive? Path difference? N plus 0.5 lambda. Okay. 2n plus 1 lambda by 2. Yeah. So you need lambda by 2, multiples of lambda by 2, odd multiples of lambda by 2. This is what you need. Lambda by 2, 3 lambda by 2, 5 lambda by 2. Very good. Okay. So basically this works on the path difference. If the path bit difference, so they will take one light, they'll split it into two. They'll split the light into two, and one will cover more distance than the other one. And then they would look at the interferometer, the fringe patterns, and that fringe pattern would give us what kind of distance it has moved. So basically, that's how you do it. So basically, if there's a distance between the two, you would know how much, what would be the, so you can precisely locate what distance has moved depending upon. So ideally, you could do with this. If you do phase shift, you can go even lower than in this. Typically, you can do lambda over 4, but if you do phase shift, you can go even much lower than that. Okay. And then there is laser triangulation sensor. This is again, you can use laser triangulation method, which basically means that there will be a light emitter, a detector, and then it detects what is the difference. So basically, the triangular path difference will basically tell you what is because what happens is, if there's a change in distance, this angle will change at the detector. So if this is here, the target moves something like this. You can see it more clearly. The triangulation sensor it determines at what location. So I have a laser diode and I have a CCD camera. So how the image takes place here will be a function of where it is reflected from. So if it is from here, the angle is different. If it is from here, the angle is different. If it is from here, the angle is different. So this detection, where the image is formed on CCD can be acquired, right? So that's how you know that where you are. So you have a reference point, and you can basically, and there's a finite measurement range. So you know that you are between this to this distance. So this can be used as so how the light falls on the CCD will affect where exactly it has been reflected from. Okay, so this thing is done in laser triangulation sensor. And then there is something called focus variation sensors, where there's nothing but it's how crisp the image you get. So what happens is, if I move, my image quality changes. So I have a finite focal length, but what I do is I keep on moving. So I can measure what distance I am. So this focus variation is more of a metrology thing than a sensing thing. So they are not used in sensors, but primarily they are used for metrology. So you can figure out where an object is using basically a focal length, a finite focal length, and a camera. Okay. So I know at what point I am in focus. So if I am defocus, I can figure out, I can move some distance and find out again when it is in focus. So basically, I can figure out that where is the exact location. So if the body moves, then I know that I'll have to move some to have another focal image, right? So I can know exactly how much motion has taken place by moving, by seeing the clarity of the image. So I'll have to move the camera to get a crisper image, and I can back calibrate how much this object has moved. So this is called focus variation. What you do is basically you can get the focus variation can be used to know what is the location of my object. Because we know that if I move, that experience you would have, right? If you take a camera, the focus is at one location. If I move front or back, or if the person moves front to back, he will get defocused. So I can know just by being in focus, if adjusting the focus, I can know where my object is. So I'll have to move my camera a little bit to know the new location, and then I know that okay, it's crisp, meaning this is the distance which the object moved. So this is called a focus variation. This is used in metrology quite a bit. So basically, what you do is if you have a free-form surface, right? What you do is you take an image at one location, the crisper image that lies there, then move the focus, take another image. So all the crisper will be on that location. So you can create a 3D reconstruction of an object using this kind of a technique, which is called infinite focus or focus variation. Okay, so this is what I had to share in this stuff. So technically the course is over. So next class we don't need to have. If you have any questions, feel free to ask me. I think officially the class is over. Today's class was just more of information to just give you some idea of what kind of these sensors and encoders are available in the market. Okay. So any questions you guys have? So the class officially is over. Thank you so much for attending this course. The only thing now remaining is the project and the presentation. I think you guys have decided to have sometime in December, so that's fine by me. And we have graded all your midsems and so what I will do is I will actually send you the averages. I don't want to share everybody's stuff with everybody. That's not a good idea. But what I will do is for every exam, I will share the class averages for quiz 1, for midsem, and also for both the presentations. I'll send you the class averages also. Presentations, of course, all of you would know because I share the I will share the Excel sheet with you for the presentation. But the other ones are already there on everybody's Moodle, right? So you'll know your grades for midsem and for the quiz 1. So quiz 1, midsem, both the presentations. These 4 things have been done. The only thing that is remaining is the final exam. If you have any questions about the final exam, feel free to ask me now. Any questions or concerns about the final exam? So there are 2 things due. Your one final presentation is due for your project and the final project report. So these 2 things are due from your side and the final exam. Everything else I think is clear. So what I will do is I will share I'll share the class averages if you would want, I can share the Excel sheet also, but I don't think that is a wise idea to share the Excel sheet of because everybody knows everybody's roll number. So that may not be a good idea since everybody has now access to their own grades in Moodle. We are updating everything in Moodle, so we'll update all your grades in Moodle, and I'll email the entire class the class averages. But if you need any other information, I'll be happy to share any information with you. So thank you for this class. It was I wish it was in-person interaction, but unfortunately that didn't happen. But hopefully we had a good interaction even with this platform. So thank you so much. So I think this officially closes the semester. Next class, if anybody wants any information, I can make myself available. Just email me. We can have a meeting if you want to. If some of you want to for discussing some things or your projects or whatever. But other than that, otherwise we're all done. Okay. Yeah. So any questions you guys have? I'm happy to answer those questions here.